The two presenters today are Kristin Hoch, who is a post-bachelor's employee at Alamos, who's been with us for the past year, and Kevin Rosa, who's in the last year of his PhD at the University of Rhode Island and who's worked with us the last 2 summers. And they've both been really helpful in testing these new variable resolution meshes. So with that, I will let Kristin go ahead.
All right, so I'm Kristin at Los Alamos, and I'm testing various variable resolution ocean meshes. And the question for this project was, how does mesh design impact simulation quality? And the motivation here was really the development of Jigsaw by Darren and Gyre, which allows us to make meshes much more quickly than we used to, which means that we can do things like make one-off variable resolution meshes or a variety of meshes for testing purposes like we've done here. And so we felt it was important to just test these meshes more rigorously, sort of see how they perform, because we're going to be using them a lot more with these new capabilities. So for this study, we used what we're calling the CUSP Mesh, Coastal US Plus. And you can see the version that I used for this study in the upper right corner. And it has 8-kilometer coastal resolution along the North American coast, a 400-kilometer wide resolution region, and a 600-kilometer wide transition region. And it's built on an EC6030 mesh as the background. We also made, on the bottom right there, a North Atlantic mesh that has 8-kilometer resolution throughout the North Atlantic. And we use this as sort of our high-resolution proxy, because a full high-resolution mesh would have been too expensive for our purposes. So for this study, we ran 10-year simulations on all of the meshes, did analysis on the last 9 years of that, and we used idealized atmospheric forcing, because that was a simpler setup and we felt a sort of cleaner study. And based on the results of this work, as well as the work done by Kevin Rosa, who will speak next, and Leanne, we came to a modified final design for CUSP, which you can see on the left here. So it has a wider area of high resolution off the east coast to encompass the Gulf Stream extension, and added resolution around Greenland and the Arctic to try to improve some of the biases in that region. And the hope is eventually to use this design in coupled simulations along with the high resolution atmosphere over the continental US as well. So for this, I did 3 studies. The first was a degraded mesh study. So we wanted to know what the effect of mesh quality was on simulations. We took an EC6030 mesh and intentionally degraded the cells. And we wanted to look at this because degraded cells show up in transition regions and in mesh seams, which I'll talk about more in a minute. And it's hard to sort of decouple the effects of mesh quality from the effects of, say, changing resolution. So by independently looking at degraded meshes, we can get a better sense of whether mesh quality is something we should be concerned about. The second study was changing the transition width between the high resolution and low resolution regions. So we tried transition widths from 10 kilometers to 900 kilometers. And the third study was coastal resolution. So we changed just that coastal resolution from 8 kilometers, which is our standard, to 30 kilometers to see if that changing resolution really did improve the dynamics. So the first study is our degraded mesh study. So on this slide, I'm just showing 2 different metrics of mesh quality. On the top here, this top row, I have the ratio of the smallest to largest side of a cell. So 1 would be a perfect polygon. Lower numbers are lower quality. So this first one here, labeled EC6030V1, is an old EC6030 mesh made with the method developed by Doug Jacobson, and the one next to it is an EC6030 mesh developed by Jigsaw by Darren. So what you can see is that this old mesh creation method has very even cells with a quality of about 0.6, so imperfect polygons, but very sort of regular. Whereas the Jigsaw mesh has these dark blue bands of very high cell quality, and then these sort of seams of lower cell quality. And then these are the three degraded meshes I use, so 0.25, 0.5, and 0.75. If you look closely at the 0.75, you'll be able to see how irregular a lot of those cells really are. The second metric was one developed by Andrew Roberts, which is the maximum percent change in cell area between adjacent cells. So again, you have the old mesh creation method, Jigsaw, and then our most degraded mesh. And what you can see here is the old mesh creation method sort of spreads out that change, whereas the Jigsaw meshes have areas of very even cell quality separated by these seams, and then the degraded mesh is just overall pretty terrible, which is what we wanted to look at. So this is the results from the degraded mesh study. I have the 4 meshes across the top, so standard and then degraded 0.25, 0.5, and 0.75, and then just a variety of different ocean metrics. And what you'll see here is looking across from, say, the standard mesh to the most degraded mesh, there's very, very little change. The degraded meshes seem to perform very, very similarly to the standard meshes. The only real difference seems to be that the variability measures, so sea surface height, root mean squared here, and eddy kinetic energy here, are slightly higher in the degraded meshes, but it's a pretty small effect. We did have to run these 2 most degraded meshes at a much smaller time step, but we think that's just because there are smaller cells present in them rather than any kind of instability. So overall, this is a good sign that mesh quality doesn't seem to have a large impact on our simulations, but this is something we should keep looking at with, for example, coupled meshes. There may be more issues with those. The second study was changing the transition width. So this white line you can see in each of these marks the center of the transition. You can see that the 900-kilometer transition, that the center of that transition is much further from the coast than this 100-kilometer transition. And what you can see here is basically the wider transition regions perform better, and they perform better even within the coastal region. That is, so the 100-kilometer transition, snapshot of kinetic energy, and I've blown it up over here. And what you can see here is you have this eddy that leaves the transition region and then sort of gets washed out. So as it re-enters, it loses that really tight current that it had upon exiting, and it doesn't really regain it. And this is something that other papers have talked about, that's sort of a known issue and something we should be aware of, that anytime you have something crossing out of and then back into a high resolution region, you're going to lose some of the dynamics in that process. The next study is looking at different coastal resolutions. So we have the North Atlantic, which is sort of our proxy for high resolution here, and then 8, 12, 20, and 30 kilometer. And somewhat unsurprisingly, the 8-kilometer here shows much better dynamics within the Gulf Stream region. You get, nice eddies and meanders, which you really don't get at all in the 30-kilometer. You don't get really any of this eddy kinetic energy that shows up. And the 8-kilometer is fairly similar to the North Atlantic, which we're using as sort of the proxy for the high resolution, which is nice to see that it does seem to help improve those dynamics. I also looked at the performance for this. So basically what you can see here is this brown line is global high res. This blue line is our CUSP 8, and or that purple line, sorry, is the CUSP 8, and the blue line here is EC6030. So it's approximately, the CUSP mesh is approximately an order of magnitude faster than global high res and an order of magnitude slower than EC6030. And a lot of that is just due to the changing time step because of the cell size as opposed to the number of added cells. Okay, so in conclusion, overall, this study indicates that variable resolution meshes are robust and that cell quality does not seem to be a major source of numerical error, which is good. One note of caution is that care should be taken with placing transition regions, that any sort of eddy formation or propagation or currents crossing transition regions could introduce issues that carry back into that high resolution region. And Kevin Rosa, who's speaking next, will talk a lot more about this. And the last thing I sort of wanted to talk about was basically, can variable resolution fix your problem? So in the course of this study and other work we've done, we've run into several situations where variable resolution is perhaps an obvious candidate to fix a bias, but not necessarily the best one. So one situation may be that the cause of a bias is not actually in resolution itself, but is in something that's tied to resolution. For example, in the Southern Ocean, we have biases that may be linked to GM, which is tied to resolution, but we may be able to resolve some of those by tinkering just with the GM and not just throwing high resolution on it, which is a lot more expensive. Also, Kevin Rosa will talk more about this situation, but we've run into situations where basically, for example, with the Gulf Stream, putting high resolution on the Gulf Stream may not resolve things if the cause of a dynamical issue is due to something else in a different location. And sometimes the cause of biases may not even be in the component. So, for example, paying attention to atmospheric effects or forcing issues is also really important. So I think going forward, these variable resolution meshes are a really good tool, but one that we should use cautiously and be aware of the potential issues with them. So I'll turn it over to Kevin Rosa, and I'll take questions at the end after he speaks.
All right, great, thank you. And Kevin, I'm going to transfer.
Hi, can you hear me?
Yep, perfect.
Okay, well, thanks a lot for having me at your meeting. So this is work I did over the summer at Los Alamos, and it's a continuation of what Kristin showed. So the overview of this talk is that we're kind of focusing in on the Gulf Stream, the path and the strength, and just looking more detailed into some of the things Kristin touched on. And the main takeaways I'll show is that we had some improvements, but also we found that the issue was a little bit more complex than we expected, and this has motivated changes to the coastal refined mesh, and we're just starting to get some preliminary results. And just the first thing I'll just cover is that one of the biggest differences is that we're using realistic atmospheric forcing. So Kristin was showing a constant climatology, and it didn't have sea ice. It didn't, it was not trying to get a fully realistic ocean. It was just more looking at the energetics. And here we're looking for high realism. And actually the cases that we compared to were published in the Peterson et al. 2019 paper, and they showed that their high resolution RRS 18:6 using this same configuration did quite well. And so the hope is that, this coastal refined mesh can approach those results. Okay, and since I was told most people are familiar with all this stuff, I'm just going to go quickly through the background, but I like this movie because it reminds us kind of what we're parameterizing in our global models. So this is the Gulf Stream separation at 1.5 kilometer resolution. And this has been a big issue in climate models and global ocean models because really to get proper resolution, or sorry, to get proper separation at Cape Hatteras, it doesn't seem like it's possible, at 10th degree, 10 kilometers. You have to go pretty fine in order to capture this. So if we can do this with, variable resolution, this could be a big benefit. And yeah, so this is just an overview of what we're kind of looking at with the structured models. And so I'm just going to skip past, and I'll show you this slide where we have the EC6030 case compared to the coastal refined and the high resolution. And we can see that the high resolution model is over 65 times more computationally expensive, but our new coastal refined is, order of magnitude cheaper than that. So this is, this could be really beneficial for improving the model without extreme costs. And we have different ways to design an unstructured mesh. So here is the low resolution mesh in blue, the high resolution mesh in red. There's also FISOM meshes I've shown that kind of trying to capture regions of high variability. But of course, what we're focused on today is this coastal refined mesh. So this is very similar to the one that Kristin showed. It does extend further up around Greenland, but other than that, it's very similar, where we have the 8-kilometer resolution around North America, and then it's an EC6030 in the background. And I'll be showing several plots, and it's always going to be low resolution on the left, coastal refined in the middle, high resolution on the right. Okay, and so the first part of the results, I'm just going to kind of breeze through, but one great application of a coastal refined mesh like this is for upwelling regions. It's a really great return on investment computationally, because these are so important for productivity. So when we're coupling in biogeochemistry and things like that. And so here's a look at upwelling off of California. So the top row is sea surface temperature, and I also showed the sea surface temperature gradient in order to highlight these filaments. And so in any low resolution model, you're not going to get realistic cold upwelled filaments, but we've seen that in the coastal refined model, we have very good agreement to the types of structures you see at high resolution. And this could, even beyond biogeochemistry, this could have impacts for atmospheric coupling and things like that. So, and also if we look at sea surface height, so, if these are geostrophic flows, you'll have flows along these contours, and we see improvements. The top row is the instantaneous, so we see more eddy activity. The mean shows improvements in this coastal current, which interacts with the bathymetry and has these persistent meanders. And we see good sea surface height variance. And then one way to quantify this, I looked at a wave number spectrum. Okay, but the main focus for the rest of the talk is on the Gulf Stream. Oops. So Gulf Stream path, of course, has been a big problem. So this is a plot of sea surface temperature bias. So in a low resolution model, the Gulf Stream is too far north typically. So this means that you have this really warm bias and then a kind of corresponding cold bias south of the Gulf Stream. And this has big effects on atmospheric coupling and all kinds of issues. And so kind of the two problems were the path of the Gulf Stream and also the strength of the Gulf Stream, the transport. In that 2019 paper, the low resolution model was shown to have a much too weak Gulf Stream compared to high resolution. So can we improve this using variable resolution? Are the surface speed. And so comparing the three models, first thing that might jump out is that the Gulf Stream width looks improved, though the strength still looks like it's weaker than the high resolution. We can already see that we're not getting good Gulf Stream separation at Cape Hatteras, but the high resolution model looks really good. And then I also show eddy kinetic energy, which as expected the enhanced eddy kinetic energy is confined to the higher resolution region. So that would be anything inside of this white line. This white line indicates the transition from 8-kilometer resolution in the coast to 30 to 60-kilometer resolution out in the rest of the ocean. Taking a second to load. But next, I also have sea surface height. Tells a similar story. I will be coming back to this plot later, though, for a more in-depth look. Here's another way of looking at that Gulf Stream path. So I show kind of the envelope of the Gulf Stream using the surface speed root mean square, but on the bottom, you can see that the individual instances, individual paths show that this coastal refined has a really persistent path where it goes too far northward, then loops down. And it seems like maybe it's being, kept inland of this resolution transition region, which would be a big problem. Okay, so to diagnose the cause of the weak Gulf Stream, I'm going to be building up this slide. So we have the Gulf Stream at high resolution in red is about 44 spare drips. And then we have this kind of wind-driven gyre contribution and the deep western boundary current. And these, as expected, sum to 0. And just down here, I show this is how I integrated the different sections of this cross section. So we have the Gulf Stream, deep western boundary current, the rest of the transect. Okay, I'm going to skip through because we're short on time. So what's interesting about separating the transect into these two portions is that it's kind of a really logical separation where they're both southward transport. So the Gulf Stream is going to be kind of the sum response to both of them. One is buoyancy driven, by deep water formation, and one is more wind driven. And really what's key for us in this modeling perspective is that the deep western boundary current is within the coastal refined region. So we might expect that to do well and the gyre to be the cause of the issues because the gyre is low resolution. So when we start looking at the results of other models, as we said earlier, the low resolution model is pretty weak and the coastal refined Gulf Stream is similar. They all look pretty good out in the coarse region for the wind-driven rest of transect, but it's the deep western boundary current, which we see is really the cause of this deficient Gulf Stream. So when we go up and look at the deep water formation regions, this starts to make sense. In low resolution, the main deep water formation regions are way too fresh and the mix layer is much too shallow. So there's no deep convection happening. And unfortunately, even though we have, for example, high resolution in the Labrador Sea here in coastal refined, we're not getting that deep convection and we're getting much too fresh surface water in the Labrador Sea. And I would argue that this is a working hypothesis, but this might be because having to do with the path of the Gulf Stream. So we had this plot earlier. This is the coastal refined mean sea surface height. And you can see that there seems to be this standing meander along the mesh transition. And this is indicating to me that there could be interactions with the mesh transition. Here's a plot of the Gulf Stream coming around the tail of the Grand Banks, and here's Labrador current water. And what can happen is that the Labrador, this is a key pinch point for trapping Labrador current water. So here's what you want to see. Here's a look at salinity at 250 meters. The Gulf Stream extension is away from the tail of the Grand Banks, and the Labrador current can bring that cold, fresh water around. Unfortunately, in our coastal refined model, we're seeing that the Gulf Stream is right up against the tail of the Grand Banks. The Labrador current is not getting out, and this fresh water is just staying up in the Labrador Sea, and it's shutting off our deep convection and turning off our deep western boundary current. So just as a review of these kind of pieces, we could say that the Gulf Stream path is being steered too far inland, which is leading to the Gulf Stream impinging on the Labrador Current and freshening the Labrador Sea, turning off deep water formation, and this is leading to our weak overturning and our weak Gulf Stream. And so this is what has led to the changing the mesh to have more room for the Gulf Stream to extension to take a more realistic path. And I have, in the questions section, I have an additional couple slides to try to explain this, but I'm now at 12 minutes, so I'll stop here. Thanks.
All right, thank you both.